So, hello everyone. Happy to be here. Happy to be here to meet the people Malcolm worked for the last 30, 40 years. So my name is Philippe Ouzilleau, and as you can probably hear, I am not British. In fact, I am from Canada. I am from the French part of Canada. And the reason I'm here is not really because I was a colleague of Malcolm, I was not a student of Malcolm, but he still had a great impact on my career, and I wanted to come here to show what his influence and what his example set for me when I did my PhD, when I started my PhD 4 years ago, and that I completed last January. So the work I'm doing is essentially to answer an age-old question, which is why some carbon may or may not graphitize. So this work is done by me, obviously, but I also closely work with Dr. Malcolm Heggie. I'm sure some of you know about him. And here you can see a little bit of all the history of carbon modeling in terms of what is graphitization and why some carbon may or may not graphitize. So my PhD was an attempt at doing a thermodynamic model to explain why some carbon may or may not graphitize. And Malcolm was very interested in this work because as it progressed, it was becoming increasingly clear that defects played an important role in graphitization. And of course, that's one of the field of expertise of Malcolm. So his input was greatly valued over the years. I would have hoped to work with him as a postdoc in the coming years, but obviously this will not be possible. But it's still a great honor to be here to discuss the findings I have made during my PhD. So the topic of the day, as I said, I'm from Quebec, so I don't know if anyone here went to Canada or Quebec. This is obviously what it looks like during the winter in my university. And in Quebec, what we do when we're in family is that we go camping and we like to roast marshmallows. So essentially, when my mother asks me what I do in my PhD, I say I roast marshmallows. Except it's not like this, but in the oven at 3,000 degrees Celsius. But the principle is more or less the same. So this is the graphitization process. Everyone knows about it. You take a carbon material, which is really raw. In this case, you can say sugar. You eat it, and you obtain this black powder, and then you can use it to make all kinds of technological carbons. Here in Quebec, the main technological carbon is not nuclear graphite. It's electrodes for the aluminum industry, but there's a lot of parallels between the two processes and the two applications. So this is why it was easy for me to make some interesting discussion with Malcolm. So to graphitize or not to graphitize. So to study graphitization, I chose to study the D002 property. So this is the average interlayer spacing of a graphenic crystallites. So if you take a carbon material, let's say the red one, and you heat treat it at various temperature, you will obtain such values, and if you take another carbon material and you heat treat it at these temperatures, you will get these values. So, in terms of the blue values, this is the result of the graphitization heat treatment for non-graphitizable carbon. There's a clear distinction to be made between graphitization heat treatment and graphitization per se. Graphitization will yield a graphitic carbon. Graphitization heat treatment will yield a non-graphitic carbon. So I know this is a little bit tricky, but it's important for the clarity of the presentation. So here, as I said, you have the graphitization heat treatment of a non-graphitizable carbon. And below, you have the graphitization process of a graphitizable carbon, which yield a graphitic carbon. So essentially, it's why some carbon will follow the red trend, why some carbon will follow the blue trend, and why everything in between exists. This was the main research question of my project. And essentially what I attempted to do is to develop a thermodynamic formalism to try to predict the graphitizability of some carbons. So first of all, when modeling graphitic carbon and non-graphitic carbon, you have to define a structure. So this is the structure that I chose to consider my model. You have essentially at the mesoscale LMOs, which are local molecular orientation clusters, which were first proposed by Madame Dr. Agnès Oberlin of the French carbon group. Between these LMOs, you have grain boundaries. Inside an LMO, you have what I call coke crystallites, which are local idealized graphenic crystallites. And between these crystallites, you have intercrystalline matter. So this is the structure that I consider for my model. This is how I can, after that, use some thermodynamic equation to try to make valid prediction. So as you can see, you have the geometric parameters of the crystallites, La and Lc. But here in the model, I will focus solely on D002 because it's the most reliable property to measure graphitization. So the key hypotheses of the work are as follows. First of all, we suppose local equilibrium hypothesis at the local scale for crystallites. So as I said in my structure, you have LMOs, which are very big entities, and you have very small crystallites. What's very important for the model to work is that you can consider that at the scale of a crystallite, the system is in equilibrium. Even if at the scale of the LMO and even bigger, the system is not at equilibrium. Because of course, graphitization is not an equilibrium process, and graphitizable carbon and non-graphitizable carbon are not equilibrium species. The equilibrium state of graphite under normal temperature and pressure is perfect graphite with absolutely no defects. But still, in industrial application, we will have both material that exist. The second hypothesis is that the Gibbs energy of a graphitizable carbon is for a sufficiently large La solely defined by the Gibbs energy of its composing crystallites. And finally, that if you look at the D002 function as a function of temperature, which I showed here, we suppose that it's only defined by the change in structure inside the LMOs. So the MGBs are composed of defects which are frozen and which will never graphitize. Any graphitization only proceeds in LMOs. So these are the three main hypotheses which define the rest of the work. So after that, we can do a simple geometric model for the mass balance of the system. Here you can see a single graphenic plane, and for given values of La, you can make it as big as you want. This is to represent the effect when heat treatment is applied of the growth of the crystallite for different increasing heat treatment temperature. Below, you can have the associated mass balance equation. So if you know La, you know everything about the geometry of your crystallites, and you can know the exact composition of it as a function of the species that you put on the gray, blue, and red hexagons. After that, what we do is that we estimate the Gibbs energy of the composing species which can go on each of these hexagons. We use a simple additive formalism with a thermodynamic path to estimate both the enthalpy and the entropy. And after that, you use this final equation, which is very simple. It's only big because there's a lot of precise terms to be written. But essentially, is you put this one here, and this one here. You sum it all, and you estimate the Gibbs energy of the entire structure. After that, you stack them up, and then you obtain the Gibbs energy of your co-crystallites, which, based on our second hypothesis, will define the Gibbs energy of the graphitizable carbon. After that, we can apply this model with the Gibbs energy software for the minimization of the Gibbs energy of the system. And here you can have the hydrogen content for a given value of Lc, which is about the same as La, of various co-crystallites as the function of the temperature of the heat treatment. So if you take a given carbon material and you heat treat it at this temperature, and if it develops this kind of Lc, you will have this hydrogen content in the system. And you can see this comparison with the experimental results, which is encouraging. You can do other application for this basic Gibbs energy model. This is another comparison between the relative Gibbs energy of the co-crystallites and something that can be measured in an experimental apparatus using a solid-state electrochemical technique. As you can see, the result more or less within the experimental error are in agreement. Unfortunately, there's a problem with this model, and this is the problem that my PhD focused on. If you convert the Gibbs energy equation into a surface energy model for this prismatic surface, which is in red in the figure, what you obtain is that there is a fixed temperature where the surface energy reaches 0 at about 2600 Kelvin. So this problematic was hard to interpret, and at the end of my PhD, what I realized is that it was related to the graphitization of carbon materials inside NMOs, which yielded a second model, which I will present in the following slide. So the interpretation is, if local equilibrium hypothesis is valid at the scale of a crystallite, for a given graphitization process with fixed heating rate and sufficient fixed holding time, that is, you only try to model a single graphitization process with a single heat treatment time and a single value for the holding time at maximum temperature, then the null value for the surface energy should be interpreted as a null difference between the density of the intercrystalline matter and the post-crystalline phase. So basically, the two entities of the LMO merge together and become a single body at this temperature. So I made the calculation for the prismatic surface at around 2600 Kelvin, but other people, such as Abrahamson, made a similar calculation for the basal surface energy at around 2500 Kelvin. The exact temperature is not very important. It's the existence of this temperature, which is. So at the end of the day, I decided to develop my graphitization model considering a critical temperature of 2550 Kelvin with an error bar of 50 Kelvin. So to do this, you have to develop a cartoon, you have to develop a scenario which will be used to model graphitization. This is the one that I proposed. First of all, you have your structure below a certain temperature threshold of about 1700 Kelvin. This is your starting structure. Then, as you heat it up, the density difference between the intercrystalline matter and the cold crystalline phase will start to diminish. So as it does, defects will be generated at the interface between the crystallite. These defects are called ATD in the sense that these defects are not frozen. When they are heat treated, they will be able to be removed, and as they are removed, they will induce graphitization in the sample. So as you continue to increase the temperature, and you reach the critical temperature of 2550 Kelvin, both the intercrystalline matter and the cold crystalline phase have completely merged, and all you have is a single body inside the LMO, but this body might have or might not have annealable topological defects in its structure. And as you heat treat it at higher temperature, these defects will progressively anneal, and at around 3400 Kelvin, all defects are removed, the material has finished graphitizing, nothing will change even if you heat treat it at higher temperature. So this is the scenario of the model, this is how we represent it. After that, the challenge is to make a mathematical approach based to represent this mechanism. Fortunately, we can use thermodynamics because the local equilibrium hypothesis is assumed to be general, to be acceptable. And if we do that, we can use an order parameter and some differential equation related to the change of D002 in the critical region between 1700 Kelvin and 2550 Kelvin to essentially implicitly integrate in the model the average activation energy for the annealing of the ATDs during graphitization. So this is more or less what the differential equation will look like if the ATDs are generated but not necessarily consumed during the critical region. That's why the delta is very small. If the delta is much larger, the differential equation will change. Yes, some defect will be generated by merging, which is represented by this term, but they will also be consumed. This is why the negative sign is applied here, and this is why here we have a positive sign. So at the end of the day, you take all these equations and you combine them together, and what you get is a model which allows you to calculate the D002 function of a graphitizable and non-graphitizable carbon simply as a function of the D002 at 2070 Kelvin and the D002 at 2400 Kelvin. Because the difference between these two values will give you the intensity of the graphitization, which is implicitly used to calculate the activation energy of the ATDs, and a singular value will give you more or less the average disorder in the structure. So now you can apply it to experimental results. As you can see here, you have the graphitizability of various asphalts. This is the experimental result, and you select the value of D002 at the T alpha temperature and D002 at the T beta temperature, and you get this prediction. If you change the value of Tc, you get this kind of lens, and you can repeat the exercise for various kinds of asphalts to see that the spectrum of graphitizability is more or less acceptably represented by the present model. So what we did after that is that we extended the application of the model to a lot more graphitizable carbon, which I will not show here for the sake of respecting the time. But what's interesting is that the model seems to work as well as for pyrocarbons and other carbons which are more typically obtained from classical process, such as the heat treatment of petroleum products. So there seems to be a parallel between the two mechanisms for the graphitization of classical carbons and pyrocarbons, which is both captured by the present model. Also, what is very interesting is that if you take non-graphitizable carbon and you apply the same model, you get more or less sensible prediction of where graphitizability will stop, where is the limit for a given carbon material. Here you can see for graphitizable carbon that there is some kind of disagreement in this region between the model and the calculation, but this is to be expected because usually in a typical carbon material, the pure carbon state is only reached at about this temperature. Below this temperature, the graphitization process is usually still influenced by the release of heteroatoms such as sulfur or oxygen. Only at these high temperatures the model and the experiment agrees, and this is because at this point and from then on, only carbon is involved in the graphitization process, and obviously right now the model is only limited to pure carbon materials. So in conclusion, a new model was proposed to model the graphitizability of some carbon between 1700 Kelvin and 3400 Kelvin. To extend the model, what would be very interesting is to link the equation to properties developed following primary carbonization at extremely low temperature, relatively speaking, of 600 Kelvin. Because if this is possible, you could take any carbon material, heat it up at 600 Kelvin, measure some properties, and then without the need of graphitizing the material, you could say it will be a graphitic carbon, it will be a non-graphitic carbon, or anything in between. So this could save tremendous time in developing new materials for various applications. And another development which would be very interesting is, especially for the nuclear industry, as I said, my PhD focused mostly on studying graphitization, which is turning a non-graphitic carbon into a graphitic carbon. Your problematic is not in this direction. What you do is that you take a graphitic carbon, and when you irradiate it, you turn it into a non-graphitic carbon. And there was someone, Dr. Mozeski, I think, wrote somewhere that the two processes are basically more or less the same. One is graphitization, what I studied, and what you do is degraphitization. So what would be interesting is to study if the equation that I developed could be applicable to the degraphitization of irradiated graphite, especially in view of the important properties, thermal properties, which are necessary for the safe operation of reactors in the next generation of the industry. So thank you. So this is, as Chris said, my whiteboard that I did with Malcolm last year when I visited him in Exeter. It was a really fun exercise. I'm only sad that it will be the only one. So some reference, and thank you very much.
Questions? Chris?
Do you think it's possible to link your parameters here with the sort of models that chemists, well, these electrodynamic models, because the fitting of the different parameters? Do you think there is scope for linking these different scales?
Yeah, right now I do not do the explicit calculation of the activation energy of the defect. I do it implicitly based on this intensity of graphitization, which is the delta parameters. But what would be great is to link this with explicit calculation of the activation energy, see exactly what kind of defect anneals. Is it at the ends? Is it a single vacancy? Is it a buck and rock, the big curve? Because there's a link between the. If I could do that, I could better understand the mechanism of the graphitization process, and in extension, the degraphitization process.
I don't know much about how these things are actually made, how graphite's actually made, but I know it's got all sorts of pitch and stuff in it. I mean, can you give any kind of tips to manufacturers from this kind of model as to what they should do in order to get, certain qualities of graphite, or is it too theoretical for that?
No, it's usually you want to have as low as possible sulfur. Usually, to make graphite, you need a big coarse particle, a coke, for example, petroleum coke, and you need a pitch.
Yes.
What you want to be sure is that your pitch and your coke has as low sulfur and oxygen in it as possible, to make sure that it gets as graphitized as possible. And after that, it's more about when you get these base components, it depends on the application that you want to do for it. Like for nuclear graphites, you have to really take care to have very dense structure, but it costs a lot of money. For us in the aluminum industry, we make it a little bit cheaper. Okay. But it really depends for the molding process on the final application. But impurities is the key for quality.
When I was a student a very long time ago, I was asked if I could help in the London School of Dentistry because they were bringing in very high-speed drills in the 1960s. And the dentists were concerned as to whether these drills were burning the teeth as they drilled them. And I couldn't help. I tried all sorts of things with. Anyway, they didn't work. But could you, by looking at the material on the drill, work out what the temperature got to because of the balance of the graphite and the non-graphite content?
Yes, if you measure okay, your tip is made of graphite. Is that it? If the tips is made of graphite, you could measure the D002 and estimate the temperature, the maximal temperature at which it was exposed during the drilling.
I think that the drill was
diamond, probably.
It's the tooth that would have the carbon.
Is the tooth?
It's graphite. I think they're pyrolizing the organic material in the tooth.
Oh, okay. In the you want to look at the tooth. You would need to extract the tooth from the patient. I'm not sure you would like that.
Okay.
Yeah, if you take a tiny bit, you could do some XRD to estimate the temperature based on the LA or the D002 by XRD. Yes, you could.
We won't go into that. Okay, so thank you very much, Philippe.